hypothalamus artificial intelligence, Cisneria engineering, and Gurobi optimization. Present. Public systems passenger transport by railways. Hypothalamus artificial intelligence, Cisneria engineering and Gurobi optimization have agreed on a technology alliance to jointly provide services to the special transport sectors, based on highly complex mathematical models. The technological capabilities of the three companies, in artificial intelligence and mathematical programming, make them ideal partners to face the multiple challenges that exist in advanced analytics applied to the transport sector. Due to the experience of the two companies, this alliance is particularly strong for the optimization of special transport systems such as the aviation industry, planning and operation of ports, and rail systems. The optimization-based applications for industries travel and transportation have been around for many years, due to the complexity of the business. The main services are workforce management, crew and drivers planning and scheduling, and staff rostering and scheduling. Fleet management, fleet planning and dispatching, network planning, and timetabling. Asset management, airport resource allocation, crane scheduling, vehicles maintenance, and warehouse resource scheduling. Yield management, pricing, and dynamic packaging. The benefits of operations research applications are cost takeout and operational efficiency, reduce costs of capital and cost-intensive resources and assets, capital expense avoidance or deferral, and better use of limited resources. Optimized workforce and improved customer service, increase quality of service and reactivity, more on-time deliveries and responsiveness, and improve employee effectiveness and satisfaction. Measurable ROI and improved profit, increased revenue and improved revenue mix. Improved market agility and reduced risk, respond to change quickly with improved planning. Smarter, greener planet, less carbon emissions and lower carbon footprint. Below applications of operations research in railway sector are presented. Metro systems. Optimization of the design of railway lines. Given the dynamics of the metros and commuter trains, this process is permanent, since new railway network lines are constantly being built. The planning of the design of railway public passenger transport lines must be based on a decision support system, which allows evaluating a wide range of alternatives and providing all the necessary information to make the best decision. Given the dynamics of the metros and commuter trains, this process is permanent, since new lines are constantly being built in the railway networks, new and existing. Three models are integrated to support this process. The first model will be called LogFin. It is oriented to define the investments to be made in infrastructure necessary for production. It corresponds to a dynamic model that defines, for each period of the planning horizon, the investments to be made, and the network for short-term operation. As input parameters, the decision maker should consider investment costs, rate of return on capital, borrowing costs, the payment period, and other financial considerations. Model constraints are related to investment logistics and financial risk management. The main results of the model are NPV, net present value of investments, VAR, value at risk of investments, cash flow, and design of supply chain networks for the first periods. The second model will be called SANDOP. Its goal is to simulate industrial operations for each possible network proposed by the investment model, LogFin. As input parameters, it should consider, at least, the forecast of demand for final products, supply of raw materials, operating costs, and sales prices. The model can be extended to consider other aspects such as technological innovation, which affects the productivity of the future processes, new technologies, which may affect market prices, and others that are considered convenient. In general, all input parameters are uncertain, and it is appropriate to consider this to make the mathematical problem a scenario-based stochastic programming model. This feature makes the LogFin model a coordinator of the evaluation of the scenarios to be considered in SANDOP. It corresponds to a dynamic model that defines, for each period of the planning horizon, industrial operations, and Material warehouses. In certain cases, it may not be necessary to consider the storage of products, because it may have little impact on investment costs, and additionally, it may be considered that the raw material offering is always provided by the market with stable prices. The constraints of the model are related to the industrial production process. Normally, there are several alternatives to simulate this process. At one extreme, we can formulate a very simple model, perhaps a few aggregate equations, which synthesize the process. At the other extreme, we can formulate a detailed model, which simulates the processes with great certainty. The decision is up to the modeler. What is certain is that the available computer technology, computers plus mathematical problem solvers, allows very advanced models in this aspect. Therefore, the level of detail will grow exponentially in the coming years. The main result of the model is the operational simulation for each period for each scenario. Data that are necessary to evaluate the function of future costs, which generate the decisions of the present. The third model will be called ALM, Assets and Liabilities Management. ALM is a consolidated modeling methodology, which focuses on the financial modeling of companies. Its growth is generated at the end of the last century, in the financial sector, as a result of the Basel Accords. ALM considers the results provided by the LogFin and SANDOP models. Minimum ALM modeling should be geared towards assessing net present value, for a pre-established rate of return on investment. Subsequently, for lines with transverse operating conditions in the urban metro system, operation schemes are designed between lines, under all possible combinations. According to the volume of passenger flow that cross trains can carry, the best ranked operation plan is recommended. As an example, the results show that, in the Chengdu Metro network, the Northern Railway Station, Zibo City Station and the Southern Railway Station have the highest transfer demand. The transfer demands that can be made by cross trains are 23,934, 16,710 and 13,024 trips per hour, respectively. The proposed design method accurately and reasonably filters stations and transfer lines, with an urgent need for cross-line trains. Chengdu Metro Timetable Optimization at Shpu Station. Shpu is a transfer station between Line 2 of the Chengdu-Dujiangyan Intercity Railway and Line 6 of the Chengdu Metro. The optimal timetabling at the station aims to reduce passenger waiting time and energy consumption through optimal train scheduling, which has a great impact on improving the quality of service and the energy efficiency from the operational point of view. From the spatio-temporal distribution of passenger flow demand, the optimal metro schedule for transfer passengers is determined by means of a multi-objective programming model consisting of three minimization criteria: timetable, energy consumption; wait timetable, the waiting time of passengers at stations; and TWT timetable, the waiting time of transfer passengers at transfer stations. These schedules maximize energy efficiency, quality of passenger service and transfer efficiency, respectively. The combined use of the three optimized schedules guides real operations. Energy-saving strategies consist of modeling four phases of speed control: acceleration, cruising, inertia, and braking. On the other hand, the operations at the transfer station are modeled in detail, considering three processes: boarding alignment, and arrival of passengers. Metro de Madrid, Metro, optimization of staffing, train depots and lines. Metro needed better planning, knowledge and management of operations, to optimize resource scheduling, considering the large number of rules and limitations involved with labor policies, such as vested rights, shifts, breaks, union agreements, etc., and industry regulations. The planning must consider all the variables that have an impact on demand forecasting, such as weather conditions, vacations, breakdowns, seasonal variations, cultural and sporting events, etc. Using optimization software for scheduling, and real-time visualization for supervision, Metro has optimized in real-time two core business operations: staff assignment, and management of train depots and lines. Optimization software helps ensure that the 565 million riders Metro serves annually benefit from more responsive transit service and better managed operations. Metro has improved resource management, scheduling and adaptation of employee preferences, significantly increased efficiency in staff scheduling and train management, develop traffic plans faster and give passengers advanced traffic status, react faster to exceptional conditions, offering higher levels of customer satisfaction, and improve the quality and speed of decision-making. Netherlands Railways optimize the rolling stock allocation. Netherlands Railways, the nation's largest and Europe's busiest, 16.2 billion passenger kilometers by 2008, needed the ability to manage more trains and passengers within its 2008 infrastructure footprint. Netherlands Railways and IBM develop powerful algorithms to resource planning that can adapt scheduling and rolling stock allocations to short-term fluctuations in ridership. The mathematical tool was called ROSA, rolling stock allocation. With ROSA, Netherlands Railways can create an optimized operating plan that maximizes service quality, minimizes costs, and provides guidance for future infrastructure investments. The business benefits was $27.1 million in annual cost reduction through the optimization of rolling stock allocation, incremental revenue gain of $54.2 million through new approach to timetabling, 2% increase in on-time performance, shorter lead time for the development of new rolling stock allocation plans, and ability to accommodate additional ridership, growth with minimal new infrastructure investments. Société Nationale des Chemins de Fer Français, SNCF, optimize rolling stock maintenance scheduling. SNCF developed a scheduling of locomotive maintenance operations model, based on a mix of traveled distance and time. The system functions are long-term scheduling for budget analysis, 1 to 2 years, medium-term scheduling for workload, 1 to 8 months, and short-term scheduling, 1 to 4 weeks. The benefit: the mathematical model allowed SNCF to save 10% of maintenance costs. Japan Railways East uses optimization for Shinkansen timetabling. The Shinkansen, colloquially known in English as the bullet train, is a network of high-speed railway lines in Japan. Initially, it was built to connect distant Japanese regions with Tokyo, the capital. Beyond long-distance travel, some sections around the largest metropolitan areas are used as a commuter rail network. The main features of the system are dynamic replanning of the Shinkansen lines in case of an unexpected failure, recomputes a schedule that minimizes the total delays. Development of the optimization model took 1 year, and scheduling engine optimization solved the problem around 20 seconds, for 300 trains per day, on 4 crossing lines, servicing 37 train stations. The main benefit are savings in total train delay time is up to 50%, and savings in recovery delay is up to 50%. Train maintenance optimization. 4 problems are fundamental in the maintenance of railway systems: detection of failures of industrial assets, the maintenance scheduling of locomotives and wagons, planning the use of workshop space, and optimizing spare parts inventory management policies. To deal with these problems, the use of artificial intelligence, in its different forms, is mandatory due to the complexity of the systems. Prognostics and health management, PHM, are one of the main protagonists of the Industry 4.0 revolution. Its function is to efficiently detect if an industrial component has deviated from its normal operating condition, and predict when a failure will occur, decreasing the probability of failure events, and determining the probability distribution function of time until the next failure, thus improving the level of safety of industrial machines. In accordance with modern trends in analytics, PHM tends to distribute and parallelize the processing of the information obtained for all the assets of a system. Given the current power of computing, it is possible to implement specific maintenance management functions in a component, subsystem, or system, on-board layer, in such a way that the coordination of all elements is carried out at a higher level, ground layer. The advantages of this approach are not only limited to processing speed but extends to component autonomy, or increases system reliability. The technological tendency of the PHM methodology is to produce closed PHM systems, and coupled to specific components, so that they perform, in a distributed manner, all the PHM processing required to control the component. This is feasible due to the computational power of super microcomputers, which, making use of edge computing, can perform complex processing, and whose size facilitates them to be part of the remote equipment, measurement and data processing. A closed PHM sensor is a collection of one or more different sensors that acquire data, processes and analyzes the data, stores the information, and has computing capacity to solve local operation problems. The figure presents the case of a closed PHM system in the railway industry for the diagnosis and prognosis of bogie health. Inside a bogie 4.0 you can find artificial intelligence algorithms to forecast the state of the physical components of the bogie, fundamental information to detect online possibilities of failures. This information is transmitted to a control center on the train for coordination of all bogies, and to a maintenance control center of the company to adjust the parameters required in the planning of short and medium-term maintenance. The figure presents the case of a closed PHM system in the railway industry for the diagnosis and prognosis of bogie health. Inside a bogie 4.0 you can find artificial intelligence algorithms to forecast the state of the physical components of the bogie, fundamental information to detect online possibilities of failures. This information is transmitted to a control center on the train for coordination of all bogies, and to a maintenance control center of the company to adjust the parameters required in the planning of short and medium-term maintenance. Programming of activities in the workshops. The optimization of the activities that must be carried out in the maintenance workshops are optimized under the approach control of projects with limited resources, in which each maintenance of an asset is associated with a project that must be optimized through a mathematical model, which integrates maintenance projects for all assets that share one or more common resources available in the workshop. More detailed information can be found in a specialized video. Planning and scheduling of maintenance activities. The optimization of the maintenance of the components of an industrial system is a general case of industrial production systems, therefore, it includes the railway sector as a particular case. The optimization of the planning and scheduling of maintenance inputs aims to define the dates on which industrial assets, locomotives, wagons, railways and complementary equipment, will be subject to stops for major maintenance, in order to minimize the costs due to maintenance assignments, including their impact on the operation. The optimization of maintenance is carried out considering, among others, the following aspects: the demand for transport services, maintenance costs, and the resources used in maintenance processes. The simulation must ensure the coordination of maintenance activities with operational activities. The result is a program of activities displayed on a Gantt chart. The following describes the artificial intelligence models, which are required as decision-making support. They are all connected to each other, as the results of one model are part of the input data of another model, in the decision-making chain, that supports asset maintenance planning. The proposed models are presented in the image. The starting point of planning is the asset information system, which is assumed to store all the information required for management, and asset histories, which include intelligent measurements obtained from the PHM system. Initially, two models are required that determine the maintenance environment. DEM, forecasting demand for products and services, and INV, spare parts inventory policy management, stochastic optimization model. PHM provides the remaining useful life, rule, and other parameters of the state of the assets, result of the PHM process. GSMC generates synthetic scenarios of asset failures, according to the failure probabilities estimated in PHM, to be used in the OIAM model. OIAM, optimization of individual asset maintenance. stochastic programming model, which is run individually for each asset. As a result, for the next planning horizon it produces two sets of assets. OSA-P, assets that can be operate, and OSA-M, assets that must go to maintenance. SANDOP-OWN, joint planning of the operation and maintenance of the asset network. Deterministic optimization model, which runs simultaneously for all assets of the production system. Its objective is to select, from the OSA-P set, the assets that need to be used during the next planning horizon. MOS, optimization of the scheduling of maintenance operations in the workshop, for the assets of the OSA-M set, and of the assets not selected by SANDOP-OWN. Receives as input the status of the spare parts inventory, and SCHED, scheduling of production operations, including selected OSA-P assets. OWN model of each type of production system. Energy savings in train control optimization. The need for a clean environment is based on a rational consumption of energy. This covers all industries, and in general all human activities. Optimal train travel speed planning involves mathematical modeling to minimize energy consumption when the train has a predefined maximum arrival time. First, it must be considered that all industrial processes are variable speed, and that energy consumption, depending on the speed of the process, is nonlinear, it is exponential. This implies that, in the absence of economies of scale, the regulation of the speed of industrial processes is fundamental in the process of controlling energy consumption. Production facilities do not have a defined capacity, it is set according to the speed of the process, and the time that this speed lasts. That is a decision variable of industrial operations. The table presents the energy consumption versus speed of the AB103 high-speed train. The column 2 shows the kWh consumed per kilometer for 3 speeds analyzed. The nonlinearity is noticeable. Khmelnytsky describes the process of operating the train using a differential equation with nonlinear constraints, and used the maximum Pointryagin principle to solve the model. He concluded that strategies for saving energy in rail trains, in each section consisted of 4 phases: acceleration, cruising, inertia, and braking. Rail trains are affected by tractive force, basic line resistance, braking force, and air resistance during operation. Due to the large mass of the railway train, the tractive force, or braking required for the train to start, or brake, in a section is relatively large. In addition, a high speed of the train in one section leads to increased air resistance, which cannot be ignored. As a vehicle increases its speed, when it is operating above its maximum efficiency, the unit amount of fuel consumed increases, which implies higher variable costs. However, increased speed means increased production capacity, which lowers investment costs due to increased vehicle use. The optimal decision is not obvious. The paper Optimal Trajectory Planning for Trains Using Mixed Integer Linear Programming presents a mathematical model that includes, in detail, the resistance of the route, such as slope, tunnels, and curves, and arbitrary speed restrictions. The objective function is a weighting between energy consumption and driving comfort, but it could be minimizing the cost of energy. The nonlinear function of energy consumption versus velocity is represented by a piecewise linear function. The optimal control problem is formulated as a mixed integer linear programming, MILP, problem, which can be efficiently solved by existing solvers. The case study considered 2 cases. For the first one, the total running time equal to 5.25 minutes, indicated by T1, black solid line, while for the second case is 10 minutes, indicated by T2, red dashed line. The speed of the train is presented in Figure 1. The optimal reference trajectories and the tensile and braking forces applied are shown in Figure 2. The energy consumption with running time T2 is lower than that with running time T1, but at the cost of a longer travel time. Figures 3 and 4. It is worth to note that the computation cost is very low for this MILP approach, is less than 10 minutes in 2011. Today the algorithm must be, at least, 1,000 times faster. The figure, extracted from another study, presents the relationship between the energy consumed and the travel time. The nonlinear behavior of the function is evident. The train journey can be modeled as an interleaved sequence of three states. Braking, when the train slowed down, eliminating energy consumption or recovering previously consumed energy, which can be used later, green line. Dwelling, when the train maintains a constant speed, minimizing energy consumption, and accelerating, when speed is increased, and energy is consumed according to the situation, red line. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.